Hello everyone, welcome to today's session on data encryption standard. This is the simplified data encryption standard implementation. Data encryption standard is a block cipher with a 56-bit key length that has played a significant role in data security. DES has been found vulnerable to very powerful attacks. Therefore, the popularity of DES has been found slightly in the decline. DES is a block cipher and encrypts data in the block of size 64 bits each, which means 64 bits of plain text go as the input to DES, which produces 64 bits of ciphertext. And this DES algorithm was developed by IBM and which was adopted as a standard by the National Institute of Standards and Technology NIST in the year 1977. Here, we are using the symmetric encryption. That means the same key we are using for both encryption and decryption process. And we are using the Feastel cipher structure, which is nothing but which will go to the 16 rounds for secure encryption. It can generate the keys, subkeys of 16 different. From the main key, we are using a key scheduling algorithm. And each of the block will be splitted into the input block into two halves. The complete block will be split into the two input blocks into two halves and processes them through a series of substitutions and permutations. It provides confidentiality but is susceptible to brute force attacks due to its shorter key length. And to avoid this, we are replaced with advanced encryption standard due to vulnerabilities in modern cryptanalysis. The application of an DES is used in early banking systems, financial transactions, and secure communications. The limitation of DES is vulnerable to brute force attacks and not secure for sensitive and secure communication. This is the diagram illustrates the data encryption standard encryption process, which transforms a 64-bit block will be converted into 64-bit ciphertext block using a 64-bit key. So this is the step-by-step process of encryption. So let us take here the 64-bit plain text, the data to be encrypted in this 64-bit plain text. And 64-bit key we are using for encryption. Initially, it will go to the initial permutation. The 64-bit plain text undergoes the initial permutation where bits are rearranged according to the predefined table. In the key generation process, the 64-bit key is reduced to 56-bit keys by discarding 8 parity bits. And here we are taking the left circular shift. The 56-bit key is split into two halves, which is nothing but the 28 bits each, and both halves will be rotated left by a certain number of positions during each round. In the permitted choice 2, the rotated halves are combined and permuted to produce 48-bit round subkeys for each of the 16 rounds. And the 64-bit block is split into two halves left and right here. According to this diagram, the 64-bit block will be divided into two halves in each round. The right half is expanded from 32 bits to 48 bits using an expansion table. The expanded is XORed with the round key. The result goes through the substitution box and permutation box to produce the 32-bit output. The output is XORed with the left half. Finally, the left and right halves are swapped for the next round. This process is repeated for all 16 rounds. So this is the one round transformation here we have. So like this, it can be converted 16 rounds. The final output of the left and right halves are swapped, and finally we are getting the 32-bit swapped bits. The swapped 64-bit block undergoes the inverse of the initial permutation to produce the 64-bit ciphertext. So as a result, the encryption process is a 64-bit ciphertext, which is the encrypted version of the plain text. So the key points here we are taking is symmetric encryption. That means the same key we are using for both encryption and decryption process, and it 16 rounds here we are providing, which provides high security through multiple permutations and substitution, and crystal network structure we are applying, which ensures that decryption is simply the reverse of the encryption using the same algorithm. So this is about the key generation process. In the key generation process, the data encryption standard, the process generates 16 round keys, K1, K2, K3, and so on, K16, each of 48 bits from the original 64-bit key. So the inputs here we are is split into two halves after the initial key permutation. Each half is 28 bits. These halves are updated iteratively for the each 16 rounds. Both undergo the left circular shift here by 1 or 2 positions depending on the round number. This operation ensures the key changes in every round. In permutation and contraction, that means permuted choice 2, after the left shift, the two halves, that means each of 28 bits, are combined into a 56-bit intermediate key. In the permuted choice 2, the operation is applied to reduce the 56-bit key to 48-bit key. The 48-bit key is used as the round subkey for the crystal encryption rounds. The output is the 48-bit subkey for the current round. The updated left and right halves, which are used as inputs for the next round. As a summary, the process generates 16 unique subkeys here from the initial 64-bit key, and it can add left circular shifts, that means variability to the subkeys for each rounds, and in permuted choice 2 reduces the 56-bit intermediate key to the 48-bit round key for encryption. So this is about the key generation. Let us discuss about the programming overview. Here, in the C implementation of this data encryption standard algorithm, we are taking the input block 8 bytes of the data which is to be encrypted, and we are taking the key 8 bits for the encryption key, and we are applying the substitution box and permutation table for substitution and diffusion, for confusion and diffusion. And these are the process steps: XOR the block with the key, and we are applying the S box for substitution and permutation combinations. So this is about the program. First, we are taking the header files here. The header files we are taking stdio.h and conio.h. Okay, and we are taking the block size, key size here. The block size we are taking the 8 bytes of the block size, and key size we are taking the 8 bytes. So these are the definitions and constants we are taking. These 8 we are indicating the block size and key size in bytes. Then we are taking the S box, simplified S box. This is a table for substitution we are taking, and we are mapping with the 4-bit values equals to a new values to introduce the non-linearity. Next, we will go to the permutation table, a table which is used to permute the bits of the blocks. Next, we will use the 4 functions here. The first one, XOR function. This function performs a bitwise XOR between the block and the key. XOR is a common operation in encryption to combine the plain text and key. So this is the example one. The example we are adding here. Next, we will go for the S box substitution. So this function substitution replace the lower nibble, that is the last 4 bits of each byte in the block using the S box. And the purpose we are taking here, it adds confusion by substituting the input with non-linear mappings. So this is an example for the S-box substitution. In step 3, we will go for permutation. This function permute rearranges the bytes of the block based on the P table. And it adds diffusion by spreading the influence of each input bit across the output. Next, we will go for encryption block. In encryption block, we will perform 3 operations: XOR the block with the key, and perform substitution using the S-box, and apply permutation using the permutation table. Let us go to the main function. Here we have the main function. We are taking the input block and encryption key. Input block we are taking as a plain text, that it is nothing but the 64-bit plain text we are taking. Encryption key, which calls encrypt block to encrypt the input block. And the steps we are performing in this original block: XOR with the key, substitution, and permutation. The encryption process uses XOR, substitution, and permutation to transform the input block into a ciphertext. These steps ensure the encryption provides both confusion and diffusion. Let us implement the program. Let us implement the program by using the C. So these two are the header files we are taking, stdio.h and string.h, and this is the block size and key size, which is 8 bytes we are taking. One we are taking block size, which is nothing but the 64 bit in 64 bit plain text we are taking, and key size also we are taking 8 bytes. Then here this we are representing S box, simplified box for substitution, which can add confusion by substituting the input with non-linear mappings. Next, we will go to the permutation table. The permutation table adds a diffusion by spreading the influence of each input bit across the output. Then we will go for XOR function. Here we will go XOR the block with the key, perform substitution using the S blocks, apply permutation using the permutation table. So these are the 3 steps we can perform for the encryption. So these are the 3 we are using for encryption. Then let us go to the main function. In the encrypt block, we are taking first XOR the block with the key, this one. In the step 2, we are applying the substitution by using the S box, and apply permutation using the permutation table. So these 3 we are using, these 3 combines the above operations in sequence in encryption block. Let us go to the main function here. The main function, we are taking the input block, 64-bit plain text we are taking, and encryption key, which calls encrypt block to encrypt the input block. So finally, the steps we are performing for encryption with original block, XOR with the key, substitution, and permutation. So this is the program. Let us run the program here. So this is the output of my program. So output includes original block, here we have, and this is the XOR with the key, and this replaces the lower nibble of each byte using Xbox, that is nothing but the substitution, and rearrange bytes based on permutation table. So this is after permutation. So the encryption process uses XOR, substitution, and permutation to transform the input block into a ciphertext. These steps ensure the encryption provides both confusion and diffusion. Thank you. Thank you for attending this session.